Well, I guess it's time to start. Today we were going to review questions and comments sort of arising out of Dr. Santilli's presentation last week. And also, I guess, to discuss more generally subjects from quantum mechanics and of course, anything else that arises as we go. Jesus, you agreed last week, I think, that you would have some comments specifically about Dr. Santilli's presentation. I think we could.
Okay, I can.
No problem. And also, Dr. Santilli has proposed a short or maybe even necessarily a long discussion about the subject of entanglement in quantum mechanics. That's, of course, a very interesting subject.
So after Dr. Cruz, it's exhausted all these questions. Thank you.
In fact, some of my questions are related with entanglement. Yes.
Okay. I also have a question that I think is related to entanglement. So that seems to be our subject for today.
Down to the quantitative representation of the entanglement of particles. It's a very 1935 historical paper. It's the birth of mechanics. Everything impinges on that point, on that phenomenon.
One comment I could make that I'll say perhaps just at the beginning was that one statement that was made by Dr. Sobchak in our last meeting sort of has stood out in my mind over the week, and that was a comment when we were discussing hadronic mechanics and its as a variant of quantum mechanics, in a sense. One thing that you said, Garrett, was that the equations of quantum mechanics still apply, right? That even though we're thinking of these equations as being applied to objects that have some spatial extension, if these objects are widely separated, we should expect the rest of quantum mechanics to hold, at least as an approximation. I think that was your point. So that when we were talking about entangled particles, at light years distance, then the fact that these particles were extended in some small sense, like say the size of a proton or something like that, does not have any direct impact on the concept of entanglement in quantum mechanics per se, which still arises out of the structure of the quantum mechanical equations of Schrödinger's equation, even in the case of with or without, I guess, the isometry. It's not isometry, but isotopy. Even with or without isotopy, we should expect such phenomena to arise.
I think Dr. Santilli will have more to say about that when he speaks.
Yeah, but is that a correct sort of summary?
Yes,
of
this is
your
exactly.
Yeah. Okay. I thought that was very relevant because I think Dr. Santilli has emphasized several times that I have trouble saying the word isotopy. I don't know. Sometimes I say it correctly, and other times I don't. But isotopy doesn't. In fact, implies that one is keeping the structure of quantum mechanics in its formal structure. Right?
I disagree. Allow me to disagree respectfully. No, isotopy is,
of course,
isotopy of quantum mechanics. So it's based on quantum mechanics and preserves the axiom of quantum.
Yes.
Preserving the axiom. So quantum mechanics is the essence. when particles not entangled, as originally entangled was the case of a proton and electron in the hydrogen atom, then hadronic mechanics recovers uniquely and identically quantum mechanics for any mutual distance bigger than 1 Fermi, because the hadronic mechanics applies only for strong interaction, with the sole exception of the entanglement. But again, in the entanglement, we have a completely different situation. We have an initial deep entanglement of the particles, then they are separated, and there are other.
Okay.
But if you want, I can. I really feel embarrassed to present, because my little presentation should clarify all those issues. But I hate to do it.
Well, let's just schedule that a bit later, so that we can sort of at least put sort of the questions on the table. So that was one of my questions. Maybe Jesus, you had some comments you'd like to make?
Should avoid any discussion. Please, let's avoid it. You see, like you raised the issue of the entanglement, I was completely unable to answer that. So we'll be able to discuss anything except the entanglement. I think the entanglement should be discussed after my presentation, if possible. This
Yes.
is my suggestion. So anything except the entanglement, please. But after my presentation, yes, Chris, this is my welcome, please.
Okay, but I make some slides trying to
Yes,
press
perfect.
my my questions. I started with sorry, I need to change my screen.
Yes, I don't see the screen yet.
Good. Mm. Okay. First, I like to write some ideas about the quantum mechanics, and I like to present this in the axiomatic approach. Then there are many different approaches about quantum mechanics, but I agree that with the time running, there have been new ideas about quantum mechanics today. And I think that here in this axiomatic approach, we can find some of the principal elements of quantum mechanics. Then my first impression is that quantum mechanics today is a successful theory, and is formalized in a complete way that not is congruent with the classical physics, of course, but I think that this is one this is a new theory, and then we not expect to only extend classical mechanics or classical physics for understand all of these phenomena. Of course, in this slide, I am speaking about quantum mechanics, not relativistic. And I am speaking here about a single particle. I think that this axiom is right for quantum mechanics of a single particle. And in this way, I think that this is a successful theory because the hydrogen atom spectrometry and all hydrogenide atoms are explained in very good accuracy.
Wait, Jesus, when you say a single particle, are you saying that, for example, because you haven't introduced any notion of particle exchange or something like that? Like, so that, like we have a good, you're saying that we have a reasonably good model of, say, the hydrogen atom for the motion of the electron in some central potential. But if we consider the helium atom, we have two electrons in some central potential, and there are some phenomena that are present in the helium atom, which are not present in the hydrogen atom. Like, I mean, in particular, you know, the exchange of the two particles, the two electrons. Is that?
Yes, but this axiom works okay only for in the case of helium, for example. We need to put away one of the electrons.
But if we have two electrons, we can still write the unit vectors in terms of tensor product of Hilbert spaces, right?
Yes. But this is the point. This is the point. Because if we consider more than one particle, we need, of course, a tensor product.
Okay.
And then I think that sometimes this is included like one more axiom for quantum mechanics, because tensor product is the base of the collective phenomena of quantum mechanics.
Mm-hmm.
And I think that this is one important thing, because the tensor product have inside of the abstract definition of tensor product the problem of entanglement.
Dr. Santilli, did you want to raise a point?
I'd like to make a very brief comment on both Professor Cruz and Professor Peach, on both of you. I agree with both your view, but there needs some clarification. Professor Cruz, you stated correctly that quantum mechanics has been successful theory, not only successful, very successful. Indeed, to the astonishment, let's remember that hydrogen atom was not, even today we don't see an hydrogen atom, but this was, about a century ago. The quantum mechanics achieved a numerical representation of all the emission. That's why I was a member of the Lyman Laboratory of Physics at Harvard. This is historical, not me, of course. The Lyman law. It was the prediction of quantum mechanics was accurate to the desired decimal number. Unbelievable, absolutely unbelievable accuracy. However, you see, it is the fate of all theories to have limitations. And this is, of course, the fate of also quantum mechanics. I think Professor Page has touched the issue by finger, but Professor Page, I agree completely with everything you stated. My suggestion, because you bring into focus a transition from one particle atom, such as the hydrogen atom, to two particles. My suggestion is to really see the physics as well as the mathematics. We should go to much higher atoms, such as the zirconium. Well, when we go from the hydrogen atom to the zirconium, the difference in the theoretical prediction of quantum mechanics and the experimental data are embarrassing. We know today that the reason is, when we have many electrons. Remember, unlike the proton and neutron, they are very small. The electrons are very large wave packet. When we have many electrons, we have non-local effects that are of this wave overlapping, that are completely outside the possibility of quantitative description. They don't admit a potential. Non-local interaction with the overlapping of the wave packet cannot represent the potential. So it's structurally, conceptually. We put it also in this way.
So that's an interesting point. I mean, and I'm well. I mean, that's an experimentally testable observation, of course. And I'm not aware of any publications which specifically point out the deficiencies of the quantum mechanical description of for example, the zirconian atom. So I'm sort of, maybe I'm just living under a lack of information, but I presume, at least from the point of view of a student of quantum mechanics, that not to expect problems with the descriptions of larger, like atoms with larger number of atoms, except of course there are such issues as the exchange forces that arise because of the lack of identity of the electrons, so we cannot identify one electron uniquely, say in helium, where we have two electrons. We cannot uniquely label those electrons, and because of that, there are quantum mechanical effects, right, that need to be accounted for. Maybe, Jesus, your point was that these effects arise when you consider the tensor product of the Hilbert space.
Yes, because you can decompose the tensor product in one even part and one odd part, and then the kind of particles selected are saying to you what part of the tensor product you are going to use. But the point is this. I think that, of course, there are many problems not solved by quantum mechanics. Professor Santilli has presented some problems, for example, in nuclear physics, that cannot solve it yet, quantum mechanics today. Of course, I agree that we need a different theory for solving some of these problems. But I think that some of the problems are problems of the building a good modelation based on quantum mechanics. This is the other kind of problems not solved yet, that we need to build good models based on quantum mechanics.
By models, do you mean like on the ontology, the physical reality associated with quantum mechanics?
No. By model, I am thinking, for example, in superconducting. In superconducting, we have a good theory for superconducting for metal superconductors, but not for
For low temperatures, low temperatures,
not
right?
high temperatures.
But high temperature superconductors seem to be a difficult problem, right?
Yes, yes.
Dr. Santilli, yes.
To stay with the quantum mechanics, I would like to clarify one point. The tensorial product that you use, indeed, Professor Cruz, is fundamental, and it has many, for instance, in crystal, numerical application, in particle physics, in accelerator, many. However, back to, I would like to clarify my point, my comment to Professor Page, that to see the reality, we have to go to multi-particle. For instance, for the case of the helium, it is my personal opinion, but shared by some, but not all, that the tensorial product, believe it or not, as strange it may seem, that the tensorial product is not needed. Why? Because it's needed very much so in higher, yes, it's needed in higher number of electrons, but not apparently not in the helium. Apparently because the two, believe it or not, the two electrons, even though they have opposite charge, they orbit around the nucleus in a bonded fashion. This has been tentatively established by experiment that in the ionization of that structure, then the two electrons, they tunnel together. In other words, after you separate the diatomic atoms, the two electrons, they tunnel together, they stay together, like in a valence. In other words, the electrons have shown in a valence to basically superimpose itself, and they become a single particle. So this is now back to them. So definitely,
that's a strange statement to me. Like it doesn't sound like quantum mechanics as I understand it.
The valence exists. That's why it's very mysterious. In the valence, you have to admit reality.
Well, I'm not sure what you mean by valence. Then perhaps, like so for example, in the ground state of helium, the ground state can admit two electrons, right? So that these two electrons are in a particular relationship to each other, but they are both in the ground state of the helium atom. But we certainly like to think of those electrons as being separate, since if we ionize the helium atom, we can remove one electron at a time, in effect. So we.
Well, the complete statement is that they are, what you said is correct, but the clarification that the electrons are some of the time they are indeed separate. In other words, the fact that they are this quantum mechanics, so this is uncertainty. So my statement that they tunnel together, this is an experimental reality. They tunnel together, not all the time, a statistical number of time. In conclusion, I believe this experimental evidence that for a significant percentage of time, which is unknown to my knowledge at this moment, they are indeed bonded together exactly as superimposed, more than bonded, because they repel each other. They are superimposed exactly as it occurs in the valence. But the point again, I raised this point to emphasize that
But okay, let me just ask for clarification. No.
We have no communication. Let me finish the statement, please. So my point again is that if you remain at the helium, you do not necessarily see the limitation of quantum mechanics. You got to go to higher. I mentioned the zircon. That's what came to my mind. But of literature, you should search for the literature, the spectroscopy of heavy atoms. Only that, but you have to look at the quantity spectroscopy of heavy atom spectroscopy. Not only that, but you have to look at the spectroscopy of the light emitted by the sun. Even as today, we have been unable to represent quantitatively with quantum mechanics the emission from the sun of lines below the lowest emission, which is the line emission from the hadron. With quantum mechanics, we have been unable to understand all the extreme complexity of the emission of light from the sun. That's all I want to say.
Okay, well, the reason why I'm thinking about helium, for example, is because I want, at least personally, I'm more focused on sort of the model aspect of the issue, and not it doesn't immediately concern me that quantum mechanics may not give numerically accurate numbers, right? So it doesn't disturb me mentally too much to think that there might be some numerical differences. But what disturbs me much more is a lack of understanding, a lack of a mental model or an image of what's going on, right? So and if I go to a complicated atom like zirconium right away, then I sort of lose sight of that model, right? I mean, I want to be able to go to zirconium at some point, right? And maybe to understand whether or not the model is being correctly applied. And if the model is being correctly applied and we still see that there are numerical differences, then of course that's an important issue. But I feel uncertain about, say, if someone were to task me with actually computing the spectrum of zirconium, I would feel very uncertain because I'm not that confident of the basic tools, even for something like helium. So maybe that's, see if I understand the point of view that you were saying, Dr. Santilli. I want to understand in what sense you say that the electrons are well, okay. There are two pictures in mind that we have with quantum mechanics. One is that we have a wave and we have a particle, right, or multiple particles. And the wave in quantum mechanics is represented by the wave function, right? Which can have, which in the case of two electrons, contains like psi of x1, x2 in time, right? And so it's actually a wave over the configuration space of the two particles. But we don't really have much of a problem about thinking of things overlapping in this language. Like when we're talking about the wave function as being a function of the configuration space, then overlapping is by nature, right? So it's only when we try to separate the wave into two parts. One part of the wave for a specific particle x, and another part of the wave for a specific particle x, x1 and x2, say. And this is what, as you said, Jesus, about the tensor product and the way in which you can project from and so from the point of view of a wave picture, then this overlapping, I think that the overlapping that you're talking about, Dr. Santilli, has to be considered to be basically entanglement, I think. So entanglement says that we cannot write the wave function in configuration space as a product, as simply a product of the wave function of the two parts. Right? So the wave function is something more complicated than just the product of psi of x times x1 times psi of x2.
I isotensorial product, where the isotopic element describes the overlapping. Will be my part, my little.
But this overlapping occurs even without isotopy, right?
It occurs in the physical reality. We try
Well,
to.
it occurs in a sense because of the interaction, because of the.
Not necessarily unique. Is the first quantitative representation. Then we expect many more to come, and at least we have a first quantitative representation. Then now, when we talk, not necessarily, when we talk about the oxygen, well, oxygen is the basis of life, and the spectral emission of the exact spectral emission of the oxygen, I am not aware it has been achieved with the same accuracy as that of the hydrogen atom. No, it is still very valid. It's still a fantastic theory. Let's not understand. Quantum mechanics remains a fantastic theory, even when there are, in the case of atom, there are small, very small deviation, big deviation, 30, 40%, embarrassing deviation from theory. But in atomic structures, the deviations are small. So, Professor Cruz, I agree with your view that quantum mechanics is a fantastic thing. I call it in my paper majestic. The structure is, schematic structure is majestic, because not only achieve such a representation, but the number that you predict is invariant over time. Under the same condition, you get the same number, which is not the case in general relativity, because we have covariance. So the number, whatever number you extend, you will look 5 seconds later, it may be different. So only quantum mechanics has this majestic feature. That's why I spent 50 years in trying to maintain the axiom of quantum mechanics. Because
but that I was presented here is quantum mechanics not relativistic. I agree that quantum mechanics have not in the first formulations be used to solve everything problem. No? We know that first Schrödinger and Heisenberg formulate the basis of quantum mechanics of today, but after Dirac and after Feynman and other more, make important contributions and modifications to the first formulation of Heisenberg and Schrödinger. And then in this way, I think that quantum mechanics is like all the physics and a theory that is in constant evolution, in constant transformation. But I think that the problem of entanglement is explained correctly in quantum mechanics, only using tensor product.
Jesus, did you have more slides in that you showed us so far 2 slides?
Not too much.
Because it'd be good perhaps if we can complete your presentation and then give Dr. Santilli an opportunity to address entanglement directly.
Yeah. If we speak about entanglement, please, let's wait.
Yes, and only for introduction to this problem, I like to put here the EPR paradox, and I think that here the theory was the problem was solved by Bell experiment, and here I don't understand because I think that the results of this experiment and the confirmation after in the laboratory says that the hidden theory in quantum mechanics using classical hidden variables is not possible, because
by classical, could I use also as a synonym local hidden variables?
Yes, local hidden variables. Yeah, yes, because this in the expectation for one experiment based in these ideas in using classical hidden variables is about 0.75, and the prediction of quantum mechanics is 0.85, and these numbers are in agreement with the laboratory results. Then I think that this is in fact a confirmation of the of quantum mechanics predictions. Maybe only that in the next slide. So I have only general ideas written by the maybe in another moment I can speak about that.
Okay.
Mm-hmm.
Sure. So.
Yes, those are excellent. Yeah, well, let me make my comment. Your viewpoint, Professor Cruz, is very interesting, and because it's quantitative, so very scholar. Thank you for raising it. I appreciate it. But comments after my little presentation.
Oh, okay. I'm sorry. Maybe your audio was perhaps cut out a little bit, Dr. Santilli. I'm not sure if I got your complete statement.
Sorry, can you hear me now?
Yes, that's fine.
Yes.
I made a comment. I complimented Professor Cruz that his viewpoint is a very, very scholar, because it's quantitative. So therefore, it is a serious argument. It's not a philosophical or a technological argument. It's a very important argument. But I would like to make comments after my presentation. After I express my compliments to Professor Cruz.
Yes. Okay. Well. I think that's. And Jesus said that he had one more slide, but he would like to wait till after after Dr. Santilli is able to introduce the entanglement as an official subject of discussion. So, Dr. Santilli, if you could go ahead and do that.
Very well, so I'll try. I have two small presentations, presumably a couple of minutes each. Little movie that I will need your patience, because I will try to extract the presentation out of another video, and then I have two transparency I would like to present, in which we can make. I'm trying to access now the. I'm trying to access the. Okay, the. Let me see if I can locate it. Just a moment. Let me see if I can see the movie. I need a little with my eyes. I need your patience, please.
No problem.
Yes, that it appears that no, it appears that the movie has moved somehow away. So give me some time, please. See, I have to.
Dr. Sobchak, you're listening attentively, but you haven't made any comments. And I was wondering if, well, I know that the presentation that you made on geometric algebra dealt with the notion of spin, for example. So the notion that the wave function represented by a spinner or a Clifford, I guess, is an element of the Clifford algebra of a particular subalgebra of Clifford algebra. But this notion of dealing with more than one particle in quantum mechanics, like, for example, in Jesus' case, he talked about the tensor product. So would this mean that we would have to talk about tensor products of Clifford algebras in order to talk about multiple particles? I know that Chris Doran, for example.
People do that, but I've seen a number of papers about tensor products of Clifford algebra, but I'm not sure they're that used by that many people. The only other comment I'd like to make is that I understand that they've entangled, but 1,000 atoms together, and in fact, a little small bacteria totally entangled. So, but I don't know that such an entanglement is represented just by a tensor product or a single. Well, anyway, I'll go ahead and let Dr. Santilli.
Yeah, you mean macroscopic objects have entanglement has been observed in well, relatively large objects, because there was a general speculation that this would be either beyond experimental capabilities or somehow prohibited by quantum mechanics itself. But because we want to think of these larger objects as behaving classically, and we want to be able to set the boundary between what's a classical system and what's a quantum mechanical system. But
okay, here we have.
I guess so. Your point is, I guess, that this boundary is, where entanglement is possible is large, right? It's
Exactly.
larger. It's not limited to just simple two particles at a time situation.
It could be 1,000 atoms, could be, or even a Einstein-Bose fluid is supposedly all entangled at low temperatures.
Dr. Santilli, are you ready?
Yeah, he's going. It's good. Looks good.
Yeah, I see.
It's not the one.
I see. It looks like oh, that's not what you want.
Yeah, I just started with that arrow there at the bottom.
I'm sorry, this is supposed to be this one.
One of the things that surprised me was the experiments that demonstrated entanglement over light fibers over long distances, like so.
Yes.
By photons separated by 10 kilometers or even 100 kilometers.
Exactly, they've done a lot of
we could expect the two photons still to obey the Bell inequality, right? That they still so this was a pretty strong demonstration that the effect is not local in any relativistic sense of the word.
You see this movie?
Yes.
Do you see the movie, please?
Yes.
Yes. In a small screen only, though. Like probably you would like to, to
that's
use
right.
full screen.
Okay, perfect.
That's looks good to me.
second now because I have to prepare the rest of the presentation. Okay. Okay, dokie. So you can see Einstein, the legacy of Einstein for new. This is regarding new energies, but this is about to just select the part regarding the entanglement. So let me start it.
Experimental evidence appears to confirm the existence of one of the most mysterious phenomena in the universe.
Can I interrupt you for a moment?
Problem. Has it been worked on?
No.
Okay, go ahead.
There's a problem with your audio. I think it's too loud. At least it sounds very distorted to me when you're playing the audio.
Okay now?
So if you could, set the YouTube volume lower, perhaps.
Just a moment. How about now? Is it okay now?
Your volume is okay, but in the audio,
your voice is good, but I cannot hear.
You have to start it up.
I cannot
again.
hear.
It's okay now?
It's still rather loud. It's still rather.
The existence of one of the most mysterious.
Okay, it's good now. It's good.
That's not too bad. Yeah, that's good.
Of particles to influence each other. Evidence appears to confirm the existence of one of the most mysterious phenomena in the universe. The capability of particles to influence each other instantly at a distance. The scientific community of the early 1900s assumed that such an effect is predicted by quantum mechanics. It became simply known as quantum entanglement. But those two words have long generated intense scientific debate. Albert Einstein had questions about quantum entanglement. He noted,
I have to restart from the beginning.
Experimental evidence appears to confirm the existence of one of the most mysterious phenomena in the universe. The capability of particles to influence each other instantly at a distance. The scientific community of the early 1900s assumed that such an effect is predicted by quantum mechanics. It became simply known as quantum entanglement. But those two words have long generated intense scientific debate. Albert Einstein had questions about quantum entanglement. He noted that quantum mechanics can only represent point-like particles isolated in vacuum, and so it's unable to predict their entanglement. Possible representation of the entanglement would imply superluminal communications, an event faster than the speed of light, and that would violate special relativity. To account for such a violation, Einstein and two of his graduate students, Boris Podolsky and Nathan Rosen, jointly published a paper in 1935 that became known as the EPR argument. Their paper concluded that quantum mechanics is not a complete theory. Debate and discussion of the EPR argument continues to this day. On September 1st to the 5th, fills up the entire universe.
Sorry, I jump now. Then other parts which are in the video which are not related to the entanglement. So I jump now to the.
Consequently, the entanglement of particles at a distance occurs through the overlapping of their wave packets, as a result of which particles are in continuous, instantaneous communication at a distance through their wave packets without any need for superluminal speed. The difficult problem that requires decades for its solution is that the interaction caused by the overlapping of wave packets occurs in volumes rather than in isolated points, as solely possible for representation with quantum mechanics. Consequently, the solution of the problem requires the construction of a new mathematics known as isomathematics, which is essentially based on new numbers, new functions, new differential calculus, and other new methods, all defined on volumes, rather than an isolated point, with consequential advances in virtually all quantitative sciences, including the new conception of life and its representation via Vaugeot-Clis hyperstructures.
Engineer Simone Bergala-Barto.
This pass to know the engineering aspect of hadronic mechanics. So let me go now, if I may. I would like to go to and show the little transparency. Turn this is into equation, if I may. So okay, so let me close this and let me reopen it. And I believe it's this one. I hope I'm sure I'm correct. Yes, it is correct. Okay. So let me sorry, I'm trying to activate this and just a moment of patience. It seems to be okay. Did you see the screen?
Yes, that's good.
Okay.
Yes.
So this is basically those. I'm trying to formulate not my idea. This is an Einstein idea. Just want to clarify because he was strongly critical of the quantum mechanical entanglement. But let's see the situation. See, we are scientists, so we have to represent. Let me take this out because I cannot see the equation. We are scientists, so we have to represent equations with phenomena with equations. So this is the basic equation of quantum mechanics for two particles. As you can see, this is the Laplacian. I'm sorry. I'm sorry. I apologize with my eyes. I'm so sorry. Okay, let's go. Let's see what this is. My interpretation of Einstein's strong criticism. Einstein's position was very, very clear, and he repeated through the eye. And it is known that he fought rather strongly and vigorously with Bohr at the Salve, the meetings. There is a recording of these meetings. When I was at Boston University, the colleague John Stachel organized his papers, and you remember he read some of the fight between Einstein and Bohr on this issue. Bohr essentially, the idea also partially expressed by Professor Cruz, that that he was trying to look for a compromise of quantum mechanical representation of the entanglement. Einstein was adamant, was absolutely adamant. So I'm trying to interpret this is Einstein's viewpoint. So this is the equation of basic equation of the quantum mechanics. This is the wave function. And this is the Laplacian, the voltage, and this is the eigenvalue, is a modular, as you can see, is a modular theory. But here is the key.
I do have a question about that equation.
Please let me finish. Otherwise, a few seconds I will be through.
Go ahead.
For quantum mechanics, so let's apply this to the two entangled particles that are down here. That positively, absolutely, there is no entanglement whatsoever. There is no voltage, no potential energy, no known interactions between those two particles. So therefore, the only equations, the quantum mechanical equations that we can write for two entangled particles is here. This is the Laplacian applies to the wave function. Now, here is Professor Cruz, very important and very scholar point. Because Professor Cruz says that I can still introduce the tensorial product of the two wave function. That is correct. Indeed, I did not write it down. This psi is the psi of both particles, so it is the tensorial product of the two particles. There is no question about it. It is not the wave function of one particle out of two. No, it's the wave function of, because we started for a pair of particles. The description of two particles, see here the reduced mass. The reduced, there is no two, means the mass is for the system is reduced. So this also includes Professor Cruz's formulation. But the point is this, that there is nothing in this equation, including the tensorial product of the two particles, that explain the communications among the two particles. In other words, while the tensorial product is indeed very, very scalar and no question, and must be included. Nevertheless, this is my interpretation of Einstein view. Again, not mine, this is Einstein view. Then there is no interaction whatsoever, no known interaction that could explain the communication of information from one to the other. Remember that if we invert the spin of this particle, and the other particle is in the Vega system, in the sky, instantly that particle will instantly invert the spin. And this can only be possible if there is an interaction. We are scientists, we have to be objective. So if we find, so Professor Cruz, this is my final comment on yours. Yes, the tensorial product is necessary to formulate the problem from a quantum mechanical viewpoint, but still remains unsolved. Unsolved because we need an interaction such that we invert the spin here instantly at the distance of millions of light, the particle is. So let's see what hadronic mechanics does. What hadronic mechanics is, now I write down the iso-Schrödinger equation with full isomathematic, careful, full isomathematic, which means even the 1 divided by the mass, the inverse of the mass, this fraction is is calculated according to the iso fields. But so the equation is essentially the same. So when we go to represent the particle, so it's essentially the same as Schrödinger equation. Axiomatically is the Schrödinger equation, just with much simpler degrees of freedom in the associative product. You know that. Also notice here, this is the eigenvalue, but this is the value number, conventional normal to my iso number, but this isotope, they cancel out, you end up at the conventional. So this is conventional. Now here is the key point. When we go to the direction of two particles, there is no potential. So that's why you don't see here the potential, because I cannot write an iso-Schrödinger equation for two entangled particles because there is no potential. So the only equations that I know to write down for two entangled particles is this one, with the star here, with the modular action of an operator. In this case, it's only the Laplacian acting on this vector of the iso-Hilbert space. Then it is centered between the isotopic element, and that's fundamentally different because the isotopic element, remember, it represents concrete and explicit interaction. We know this from nuclear physics. We could not possibly achieve numerical representation of the data of the deuteron unless the isotopic element represents strong interaction, which are not derived from a potential. So you need anything else, anything you want, except the Hamiltonian for the representation of interaction. Those are contact interactions which have no potential. If you try to give a potential, here you exit from a boundary of physics because you give potential energy to interaction that has no potential energy. And this is one of the many representations that we have. The one which you have, Professor Cruz, I did not have time here, is that the tensor is not your tensorial product becomes an isotensorial product. In other words, it is a conventional tensorial product, but performed with the isotopic element. The moment you insert the isotopic element in your tensorial product, immediately you get this interaction, immediately, and you get this expression here of for the two particles. That notice that is a volume integral of the psi1 and psi2. Psi1 multiplied the star multiplication for psi2 Hermitian conjugate. So this gives you precisely the volume of the overlapping of the two different wave functions, psi1 and psi2. Notice that absolutely this is not unique. No, this is only primordial empirical representation which we did 2 or 3 years ago. And already now I'm told that there are a number of alternate better representations that are coming. But essentially, again, this psi is a tensorial, represents the system of two particles. So this is the I forgot the name, Professor Page, the iso decomposition, the iso product are different. So this is a tensorial product of the two particles. In the interactions represented by this expression. To conclude, in this, I worked 50 years on this point. I have to agree with I agree with Einstein that I could not find no quantitative representation of the interaction, not an interaction, has to be instantaneous and has to be at a distance and has to be without a potential, because otherwise I have all sorts of inconsistency, granting a potential to an overlapping that has no potential. It's like giving a potential to a balloon that is moved by the atmosphere by wind. That's contact interaction, has no potential. If you give it, like giving, it's outside the boundary of physics. Granting a potential to an interaction is not. And then you have to represent anything you want except the Hamiltonian. I prefer the isotopic isotopy because it preserves the axiom of quantum mechanics, which are majestic, and only makes them realize them in a broader way. But and rather than there are other models that totally exit from the axiom of quantum mechanics, which are certainly worthwhile investigating. But personally, personally, I'm not interested. It's excellent work, excellent research. But personally, I prefer preserving axiom of quantum mechanics. Gentlemen, this is all I know in 50 years. Please, okay. Comment.
Okay, I have a comment that I like to make, but I want to write something in my screen. Then can I?
Well, I do have a question on the slide itself. Maybe before you change the share, just to address that one question. On the first page, I think, the previous page. Yes. My question is, what is R?
R is the relative. You see, this is the equation for the bond state of two particles. So R is a good question, Professor Page. Thanks for asking. Very important. Is the relative coordinate. Indeed, the mass is reduced mass. Everything is for the. I can add
relative to center of mass.
No, it's a relative distance. This is a very important question. This is relativity relative to the observer, because this is the entanglement is observed by an observer on Earth, and those two particles are far in the sky.
But at relative rest to each other in the same inertial system.
They assume to be.
See, this is very different than the Schrödinger equation for two bodies that I learned in first year quantum mechanics, right? So in first year quantum mechanics, we would write psi of t of R1 and R2. So R1 being the position of the first particle and R2 being the position of the second particle. So in that case, it's clearly related to two particles because we're talking about the position of two particles. Of course, there is the issue of frame of reference, but this is classical, so that we can presume some absolute frame of reference. In a Newtonian sense, right? But this is really important point because this R1 comma R2 is what I call configuration space. It's also what Jesus called the tensor product, right? And without distinguishing R1 from R2, then I don't understand this equation as representing a two-body system.
It is the equation of the hydrogen atom, and then you don't understand the hydrogen atom. This is you can certainly rewrite this in R1 and R2. I wrote this an equation, the equation, standard equation for the hydrogen atom, exactly the same with reduced mass, R, relative coordinate between the electron and the positron. But there is no question about, yes, you can rewrite this you write this with a tensorial product with one psi and R1, and then you have to introduce an external observer, and then the R1 is referred to the external observer, R2 is referred to the external observer, but then what is important for the interaction is the relative coordinate, the relative distance. So you cannot escape eventually from computing the distance among the two, because that's the distance that establishes the speed of the interaction. Conclusion, yes, you can rewrite this with R1 and R2, but honestly, I do not see how it will affect the argument that you will not extract an instantaneous interaction by introducing an external observer and writing R1.
Well, yeah, so of course in the original EPR article, for example, it is written in terms of R1 and R2. And the argument about the interaction is that the entanglement implies that there is a non-local connection between the two. So non-local is maybe in this case a synonym for instantaneous or something like that. And of course, it was this non-locality that Einstein objected to. Right?
Not only the non-locality, they objected, from my recollection of the discussion with John Stachel, objected against, Einstein could not extract any interaction that will represent what you state.
Any local interaction, right? That was the point, right? That Einstein insisted that we wanted to have to describe things as being interacting in some local sense, so that there's. And so I guess when you're talking about relative distance, you also are thinking in terms of locality in that way.
Yeah, R is just a position vector. As you see in the two arrows in the picture, they're position vectors from one particle to the other, one system to the other entangled system.
But that position vector presumes that I'm not sure.
Well, look at the Laplacian. That's obviously Laplacian in what? Three-dimensional space.
And we have R1 and R2. The presentation by Einstein in the historical paper is certainly much better than this one. Why? Because the superluminous speed was with respect to the observer. I omitted this in one transparency. I omitted, but my point, however, persists. Even by formulating this with R1 and R2, and so still I agree with Einstein, there is no interaction that will explain with respect to an inertial observer on Earth that can possibly explain the instantaneous interaction one at a distance. Now back to the non-locality, Einstein was strongly against Einstein, it was Einstein. My word strongly against is wrong. Einstein, I agree with you, Professor Page, that he suspects some non-local interaction. Indeed, the interaction that we are presenting here, they're strictly this is strictly non-local. It's strictly Einstein point. Strictly, we are only trying to represent it with an equation that didn't exist before. But the point, however, that Einstein admitted, the moment you introduce non-local interaction, such as this one here, then quantum mechanics is gone, and special relativity is also gone, because non-local interaction are strictly not admitted by the topology of quantum mechanics. There is another point that I would like to make regarding, I heard about Professor Cruz, the classical interpretation. Yes, if you pass to a classical formulation, then it is much better than quantum. You have possibility much better than in quantum mechanics. And it has been recently, if you look at the physics issue of a few months ago, I can send you the reference. There was a beautiful paper by a lady, Professor Shapiro, who presented systematic evidence. Believe it or not, that's a mystery of nature. Many mysteries unsolved. Presented lots of evidence that the entanglement occurs at the purely classical level between ordinary harmonic oscillator, macroscopic harmonic oscillator. It had not been discovered before because those interactions are very, very sensitive. These are very, you need very special, highly sensitive equipment. She had, well, actually, she was a review of various, but they had this sensitive equipment. So your argument were classically supported experimentally, but then again, you exit from, then you have to abandon the uncertainty. You go to my paper of progressive recovering of Einstein determinism, but then you have to introduce non-local interaction. You go outside the quantum mechanics. You need a non-unitary transformation. There is no way that I know that this interaction needed to represent this entanglement can be obtained within the class of equivalence of quantum mechanics. Here I have to recall a very important theory about von Neumann. Von Neumann, I'm sure you agree, was one of the most important mathematicians. And von Neumann wrote what is the most powerful theorem against Bohm hidden variable. Basically, he proved that, in my view, that Bohm hidden variable cannot exist within the context of quantum mechanics. By quantum mechanics, he intended the axiom as the Copenhagen interpretation of quantum mechanics. So he proved. So you cannot, even with, the moment you represent this phenomena, Professor Page, you like prefer with an external observer down here and down to sure, but it doesn't not the answer doesn't change. The moment you try to represent with the hidden variable, then this 100% squarely within hadronic mechanics, because only hadronic mechanics produces explicit and concrete. This is the hidden variable. This is the one is hidden here, and the Hamiltonian on the tensorial product. In our case, it's an isotensorial product. Incidentally, this is the iso decomposition theorem. Namely, this iso wave function is the isotensorial product of different. Is the verification of the iso decomposition theorem.
But in this slide that we are seeing now, I don't know how you speak here about the interaction, because if I understand that the two bodies that we are here looking are distributed in the space, but the more concentration of the bodies are around the little circles of these pictures. I am right of this, because we can think in one body like one distributed mass in the space, and most of the mass are around the center. Then here,
yes, the mass is in one Fermi radius, but the wave packet is much more extended. This is a phenomenon of wave packet.
Yes, I understand. But if this is wave packet, the center interact not instantly with the other center of the other mass, because this interact only with the front wave that is arriving to that point. Then here we have one problem of time and communication of interaction here. The same problems that Einstein in the before slide are presenting. It's the same.
But Jesus, your slides initially presented the idea that the probability arises by the application of the adjoint operator to the wave function, right? So that when we make a measurement of the position of a particle, then the wave function tells us how to compute that probability, right?
Yes.
For a given measurement of a certain kind. So, for example, making a measurement of position is a particular operator, and so then applying that operator to the wave function for one of these particles tells you a density, probability density of where that you make this measurements, for example, many times. Then it tells you how frequently you're going to observe the particle being at some location. So you said if we make the measurement many times, then we will find that most often it's in the center of these circles, right? Like this is we presume this is a kind of Gaussian representation of the contours of a Gaussian or something like that. So we do the same thing for a second particle. And so we're talking about where that second particle is located, right? And so I have some difficulty understanding the notion of interaction, because these wave functions are being used to tell you the result of a measurement, right? The wave function isn't how to say this?
How about coherent? How about a laser beam? It's a coherent. You can't have two particles being coherent. So in a certain sense, a coherent wave is more concentrated, or it's a different picture than such a picture that we have.
Yeah, this is laser issues a little bit different, but because we're talking about photons, for example, and photons obey a different type of statistic when we interchange them, right? So when we interchange two electrons, the wave function sign must change. This is a rule that this is defining what you mean by a Fermi particle versus a photon that's a bosonic particle, right? So you can have a coherent wave, like a laser beam can be coherent because the particles are bosons and they can be in the same place at the same time. But ordinary matter, electrons,
like electron goes through two slits at the same time.
Goes to what?
Professor,
The double slit experiment. Electron goes through both slits. But I guess it's not coherent, though, as you say.
if I may have a comment. But first, I would like to have a comment for Professor Cruz, but then I would like to have a comment on your very deep view. Professor Cruz, allow me to express my view. Look at here. There is no front wave. Those are the wave packet as when you to see the entanglement. My God, this is my view, but this is the view also shared by many other scientists regarding the wave packet. The wave packet is represented here and is as big as the wave packet of one electron fills up the entire universe. Mathematically is identical in all only at infinity. So you have no wavefront whatsoever. No, you have no wavefront. That's the idea of the overlapping of the wave packet. There is no wavefront. That's the very point of instantaneous. This is the basis of instantaneous. And Professor Garrett, your intuition, I think hit the center. This, if we look deeper at this, if you look at what is the mechanism according to which what we state here is a very crude, primitive step, namely an interaction between the overlapping of those wave packets. Yes, this is the mathematics. But what is the mechanism? If you look at what the mechanism that actually triggers, the action on one particle to be implemented, the mechanism is precisely a kind of coherence. Those wave functions are coherent because the particles were originally bonded together. So they were born with coherent, 100% coherence in wave packet. That's the very reason why if the particles or were originally not bonded together, they have no entanglement whatsoever, none. The entanglement only occurs when the particle, think about the one hadron that decomposes into two particles. Those two particles were inside the hadron, so they were born together, and so they experienced interaction. So the coherence, yes, very, very. Of course, this coherence has no connection physically with the coherence for a laser. No, the laser is for electromagnetic waves. Here we are talking the coherence of this infinite wave packet, to my best knowledge.
Then you have one infinite object.
Yes, this is as big as the universe. Each wave packet. Remember, those two particles are separate. This is one galaxy. This is another galaxy.
Then all in the universe are entangled.
Yes. And that's the new conception of the universe. The universe is one single object, deeply interrelated.
Because in quantum mechanics, we speak about correlated systems, and all the systems are correlated. All the systems are correlated. And when we say entangled particles, we say correlated particles. And then this particle spread all the universe. The wave functions spread all the universe. Then I don't know, the problem is when Einstein introduced the question in terms of interaction and communications between two particles located in points. But here in the function of the system is not in point, because this is predicting the state of the system in all the space.
Yes, yes, indeed. Very related correlation, very related, very, very related.
But this like that's I guess exactly what I was saying, but you said it in a better way, right? That if we make a measurement of position of one of these particles, we can think of it from the point of view of having the wave function of that one particle, and then applying the operator to that wave function to find a distribution of that particle. But quantum mechanics says, though, something a little more complicated, right? It says that the wave function of two particles is a single wave function, right? Yes. Of two arguments, right? And so it's not that we have one wave function for one particle and another wave function for another particle, but we have a wave function for the system of particles, right? And so when we apply the operator, we're applying it to the wave function for the system of particles, and only under certain circumstances is it possible to represent the wave function for the system in terms of the product of the wave function of its components, right? Yes. Only very special case, right? So, but in general, the wave function for the system represents some degree of entanglement, right? So that means that when if we try to make a measurement, if we try to locate the position of one particle, then and we try also another operator to find the position of the second particle, then we'll find that they are necessarily correlated. Those two distributions are no longer independent of each other, because they arise from the same wave function of the system as a whole, right? So it's in this picture, it's hard to think in terms of one wave function interacting with another. The picture doesn't arise.
Well, then it's very difficult to understand how the proton attracts the electron in the hydrogen atom. I can apply the same, exactly the same argument to virtually our entire knowledge. Also, Professor Page, allow me to indicate what you state is correct. You see here, that's exactly what I've done. I presented a wave function representing the two particles as a whole, but here's but however, there is the decomposition theorem that then you cannot say, oh, I don't want the decomposition, even if you don't want which in your argument essentially you don't want, because if you decompose, you get some results that you would not prefer. But that's not however, you cannot eliminate the existence of the decomposition. The same here. This is a wave function representing the particle of both. But this is by a very principle, one of the axiom of quantum mechanics, that the composition of this into the tensorial product of the two individual wave functions. You cannot avoid that because it exists. It exists in the axiom. So even if you don't like it,
no, I don't. This is related to the point that I think I raised in my email, right? That I did not understand what you called decomposition as being inherent in quantum mechanics, right?
and
So I understand, of course, that superposition is inherent in quantum mechanics. Superposition meaning that if we have one wave function that solves the Schrodinger equation and another wave function that solves the same Schrodinger equation, then we can add those two together and we still have a solution to the wave function. So to me, that's superposition, but it has nothing to do with decomposition, right? So decomposition, though, was the same thing as what we were just, from my point of view, is the same thing as what we were just talking about in terms of entanglement or not entangled. So that if something is entangled, then it's no longer decomposable, right? It's no longer. But that entanglement is entirely consistent with the classical theory of quantum mechanics. Right?
If I may comment, I agree with. Incidentally, we don't use not the sum, just the tensorial product of the two wave functions. I agree with you completely, Professor Page, that those two particles are, once they are entangled, are one single body. But here is the point: you cannot represent it with quantum mechanics, because the moment you add the contact interaction, this wave function here is no longer decomposable on a tensorial product. You can only decompose it at the isotopic level, in which we have introduced the star product. Then this is the star product of psi1, star product of psi2, and so you exit completely the moment you interpret it as a single body, as it should. I agree completely. Then you exit from quantum mechanics. You only reach this representation by a unitary transformation. So when you go down to
but then this your principle of what did you call it, decomposition, like I would argue that is not part of quantum mechanics as it was originally conceived. But I could accept that it is part, perhaps, of the hadronic mechanics or the isotopic version of quantum mechanics, right? So that if we accept this as the principle, then we can look at the isotopy as being able to reestablish this decomposition, right? But ordinary quantum mechanics says that the decomposition is not possible, that this is an entangled system. So if I understand what you're saying, Dr. Santilli, you're saying that if we go to iso Schrodinger equation, then we will always be able to decompose it into two wave functions.
Iso wave function.
Iso wave functions, yes.
Let me go back. Professor Werner Heisenberg accepted in full my email, and he made comments that indeed that the axiom of quantum mechanics, in the case for the hydrogen atom, is the equation for the hydrogen atom, For the case of the axiom of quantum mechanics, Copenhagen school, that's Bohr was his teacher, and he cared about this very much so, then implies that this wave function can be decomposed into the product, tensorial product in the correct language by Professor Cruz, the tensorial product of two wave functions. And that's why in the hydrogen atom, we can study individually the one proton and the other. Now, however, that's what he agreed, that the moment you introduce some non-potential interaction, the instant you introduce a non-potential, in this case, where nonlinear, this is impossible. Now, this is the case for all, this is the case essentially for all interactions that are not from a potential. All of them implies the impossibility. This confirms your view, Professor Page, that those particles are no longer, cannot be no longer separated in our world, in our universe, in our what we perceive.
And I think that this is the problem with the Einstein argument, because he thinks that when the particles are apart, then if we made one medition in one particle, the other is not part of the system. And this is the problem. When two particles are entangled, they are in a more complex space.
Yes, the iso-Hilbert space, yes.
Much
more Hilbert spaces.
And then if they are in a more complex space, all the action and all the meditions that I can make in one part of these systems affect to other the space.
Can you repeat, please?
Yes, if we put two particles apart, but they are part of one system, more complex systems, if I make one medition in one particle, the effect of this medition affect to all the space.
Belonging to that system. Yes, yes, indeed, that's very true. That's true, yeah. But however, back here, this view of the origin of the entanglement is the overlapping of the wave mathematical represent. This view essentially implies that the wave function of those two particles cannot confirm Professor Page your viewpoint, that the particle cannot be separated. In other words, those two particles can no longer be separated in our physical space. They can mathematically separate the isospace, but the isospace is a mathematical structure, it's not a physical one. This is just a mathematical representation. This is a physical interaction. But this structure here, what I consider physical is the Euclidean space, or the real, but so this confirms that this psi can be decomposed into iso product of the isotensorial, if you want, the iso product of psi1 hat and psi2 hat, yes, but not. It cannot be consistently decomposed into psi1 multiplied by psi2. Which confirms that in the entanglement, confirms over again Einstein viewed from a new point that the entanglement is outside the possibility of quantum mechanics. You need a completion. What I propose is this is the completion, the isotopic product, but keeping the axiom and keeping everything else. But there could be other view. But the bottom line, apart from mathematical aspect, the bottom line is here. This Again, this is you can decomposing the product. That's the decomposition theory. Decomposing psi1 multiplied conventionally tensorial product psi2, and you can do it here. Introduce another observer here, but you remain. The point. That's why I support Einstein. Because we were scientists, so before claiming that quantum mechanics can represent quantum mechanics, I mean, again, according to the Copenhagen representation of quantum mechanical axiom, the claim that quantum mechanics can represent entanglement. I agree with Einstein. It cannot. There is no known formulation.
It's very strange to hear you say that, right? To me, it seems very strange because the argument that I heard, that I get from reading the EPR paper, is that it is because quantum mechanics represents entanglement. Because quantum mechanics represents entanglement, that is why Einstein rejected it, right? Einstein rejected it because he didn't think that entanglement was a physically feasible thing, right?
Show me the paper in which I stated so. Absolutely never ever stated that in paper. On my honor, show me the paper that quantum mechanics can represent entanglement. Absolutely not.
But that's exactly in the original EPR paper. Like that's exactly what the EPR paper meant, right? Was that these two particles are entangled, and so because they're entangled.
Professor Page, we have a total respectful disagreement, irreconcilable disagreement. This is against everything I know on the history of the case for Einstein. Everything I stated is to try to interpret Einstein. Einstein was that was it, the Einstein view, which I adopted, and I only formulated mathematically, but by showing that if you want to represent, if you want to have any interaction, you must exit from the class of unitary equivalence of quantum mechanics. Then you get something. You get something. But here, if you remain within the class of unitary equivalence of quantum, this is unitary equivalence of those equations. It is my Einstein view. It is my view supported. You have no chance of reaching an interaction explaining this phenomenon. If you disagree, Professor.
No. Okay, to me, you just said two completely different things.
Represented an attraction. When you look at the equation, it's an attraction.
No. Please.
Please, when I speak, let me speak without interruption. Otherwise, I feel embarrassed. And then when you speak, I'm totally silent. So please do the same to me. So I respect your viewpoint that you believe that quantum mechanics somehow, in an undefined way, is compatible with. However, we are scientists. We have to be scholars.
No. This is incorrect.
Really, if you want to really believe that quantum mechanics can represent entanglement, please, you have to identify. Here, let me finish the sentence without an interruption, please. Otherwise, we have zero communication. You have to identify an interaction between those two particles. And here's the key word: within the class of unitary equivalence of those equations. Because if you use non-unitary equivalence, you have an infinite number of models, infinite number. I presented only a class. There are many more. So this is the key point in which I insist. In other words, I don't want you to use the word quantum mechanics. Oh, I have quantum mechanics. No, you don't. You have exit from quantum mechanics on rigorous scientific grounds. I feel very strongly about this. If you do produce an explicit interaction via a unitary map of those equations, yes, then I say Einstein is wrong. You are correct. But at this moment, I have to say Einstein. Sorry for the delay. Please, any objection?
Can I make a comment, please?
Please, certainly.
In these two equations, those are not equivalent. Those are not equivalent because you can build systems of two bodies,
Yes.
and these two bodies cannot be entangled.
Yeah, agree completely.
No, then this equation that you are signaling now is not for the same system that is the equation in the first row.
Yes, very true, very true.
They are not equal. And in quantum mechanics, you can speak about entanglement because when you build a system of two particles, you use a tensor product. And in tensor product, there are more states than the states of the systems separated. There are more states, and those states are the entangled particle states. And this is the important role of tensor product in this problem, because it's like the ideals in a ring. You can find some ideals, but if you only take part of the ideals, not build all the space. No?
Yeah.
There are more.
I agree with every word you indicate. These two equations are clearly non-equivalent. That represents clearly non-different, totally different system. Here you see a potential. This represents the hydrogen atom or the deuteron represents the deuteron. This instead, this is the equation for two entangled particles. To the best of my knowledge, in quantum, the equation for the entangled particle in quantum mechanics, the best that I know. Let me finish the statement, please.
But are different systems then? And we cannot compare they, and then we cannot ask about interaction potential in the entangled particles.
No, there is no potential. No, this is that's why this is the equation for the entangled. This potential is for deuterium, deuteron, the hydrogen atom, but this is for the entangled particle. There is zero potential. The potential is zero. So, my point.
In these two equations that you are putting, we are speaking about different systems.
Yes, yeah. This is the equation, not this one. This is the deuterium, deuteron, the hydrogen atom is the two-body quantum mechanical system. This is the two-particle entanglement. There is no potential V is zero here. So you put V zero, and this is the equation, the experimental evidence, incontrovertible experimental evidence that has been measured in 1 century is that between entangled particles, the potential is zero. That's why from V here, you end up V zero.
No, Professor Santilli. The potential not is zero. The potential is part of the system.
No, but there is no potential energy. There is no electromagnetic interaction.
No, because you are asking about electromagnetic interaction because you are thinking about one communication between the two particles. And this is the problem. This is the problem. Entanglement are not speaking about communication between particles, but are speaking about correlation between the particles.
But correlation is a philosophical, from a physical viewpoint.
No philosophical, because if you interpret the system in the way of quantum mechanics axiom, they are correlated in the function state of the system. They are correlated there.
But if you put a potential here for the entangled particle,
No, I don't need to put one potential here.
Oh, you accept this equation then? You accept this equation? I did not understand. Do you accept this equation as being the quantum mechanical equation for the entanglement or not? Please let me know. Let me know.
If this equation implies a tensor product,
Yes, yeah, this is a tensor.
and then you can put this tensor product in terms of one separation of one particle in the position of one particle and the position of the other particle. Because we are speaking about the states of the two particles, and then we in the states that we are describing the particles, if we get the tensor product, then there are the one composed state now.
Yes, yes, we are in full agreement. Yes, this is a tensorial product, but even so, I do not see how the application of this Laplacian on a tensorial product can produce an interaction. I do not know how. Again, the issue is, let me reformulate it again, by clearly writing this as this quantum mechanics, strictly quantum mechanics, writing this as a tensorial product of psi1 and psi2, and by having no potential here, because there is no evidence of any potential energy, or if you add anything to the lab, you see, the moment this is, you can add it because this is the electric interaction. I have a potential energy, is an energy which is measured. So the moment you add to the Laplacian, you add something, you give energy to something. What we know as of this moment, maybe tomorrow they will discover something new. But to the best of my knowledge, any addition in this equation, or any addition of a term that implies is an energy, that you give energy to this interaction. And this means exiting physics, because there is no energy. This is an interaction. That's part of the enormous mystery. There is no energy. So therefore, you cannot add something here. And I do not know how to reobtain this interaction term by decomposing this into a product. So again, if you do any unitary transformation of this equation, we do not, nobody has been able to, in 1 century, has been able to extract and actually interact, has been able to represent this phenomenon with an actual equation, and at least comparable to what we do. Even partially comparable will be something. You see, this is the problem, is the remaining strictly within the axiom of quantum mechanics. That's
I think we can think one problem of to entangle two particles via some potential interactions. For example, in the case of particles of two states, we can say that, for example, a spin. Then how can we build one entangled state? How can we get one Bell state from these two particles? An unsinglet that you can build in the laboratory is a perfect Bell state.
Why can't R just be equal to R2 minus R1, just the difference of their center of mass, or however you want to think about it? But R in that second equation is just R2 minus R1.
You can rewrite this equation with R1. You introduce an external observer here, and then you decompose this psi1 at psi2, and then this is R1 with respect to R2 with respect to so on. But the R remains the relative distance. The R
Exactly, that's all.
I mean, it will not change the R. It will not change the wave function. The wave function here is the total wave function. You decompose it into the individual product, but the problem remains the same. The problem is that interaction having a potential energy, careful about the word energy. But Professor Page, you were about to say something.
Oh, I was going to try to comment on Jesus's at least my interpretation of what you were saying, Jesus, that we should think of the measurements as being a property of the system of particles. I think that's what you were saying. So that
Yes.
so that when we make a measurement of one particle, we're not measuring that particle. We're applying that operator to the system of two particles.
Yes.
And we are forced to do that because these, as you started with the presumption that they are entangled, right? And so that when we measure a correlation, we're not looking for how one particle affects the other, but rather we're making a measurement of the system as a whole. So I think your argument was that in a sense it's incorrect to look for an explanation of the correlation in terms of interaction, because that's not what we're trying to explain, right? Like when we make a measurement, we make a measurement of the system of two. We don't make measurement of one and then a measurement of the other and then see how they're related, right? Is that what you were?
Yes, I think you explained perfectly the idea.
Of course, it's maybe abhorrent, a bit abhorrent to the concept of reality, right? So
Yeah.
that you say, well, Einstein wanted theories of physics to be realistic in the sense that we could separate the components. We could always say that, we could always say when one thing should affect another and one thing should not. But if we insist that we have to describe the universe as a system, then there are effects that emerge from the system that are not inherent in any one interaction. Like they are a function of the overall system as a whole, right? And I guess at least mechanics at the turn of the century had insisted on thinking of connections between the parts, but like always in terms of parts, right? But
Yes.
later in the 20th century, it became much more popular maybe to think of things as systems, so that a system is more than the sum of its parts, right? And so when you do things to a system, you should expect to get different answers than if you just do things to their parts, right? This was a sort of a philosophical sort of revolution in a sense, right? And during the 20th century and it's not really fully accepted by physics, I don't think. But in all of your presentations that I've heard, Jesus, you take a very systems view of things, right? That when you talk about the state of the system, you don't talk about it necessarily in terms of how the different parts relate to each other.
Yes, in the pictures that I used to do, if we think about the interaction between two particles and one observer, of course, no? If we speak about the interaction of two particles, if we put apart these particles, we cannot break this system, because
No matter how far apart they are, they still constitute a single system.
Yes, this is the idea. And I think that this is the concept of entanglement.
Yes, if they are entanglement, that is correct. Yeah.
But
However,
Jesus is using this argument to say, well, it doesn't make sense to look for an interaction, because the interaction presumes some decomposition, right? That
that is okay. This is an escape, to avoid the problem. But okay, forget about the interaction. But then you remain with we are scientists, and we have to say, if we have to be honest, we have to reach a point in which we have to see whether we can explain the physics with one theory, or that theory is limited, incomplete, as stated by Einstein, and we have to look for a better theory. That's crucial issue. Here, to the best of my knowledge, according to quantum mechanics, this is the equation. Since we do not know the interaction, it's true, I agree completely with that indeed those are for entangled, but those are not entangled parts. This is quantum mechanics. That's the reality here. This is the reality here. This is quantum mechanics. That's so for quantum mechanics, the only way that quantum mechanics represents those particles is as two independent particles, so non-entangled, so therefore can indeed be separated, two non-separated, each one having a kinetic energy. On the contrary, here, if you go here, no, then the argument that it's a single body, yes, that's applied. We think we covered it before. Absolutely true. This is a single body, and indeed, my point was before, where iso-wave function cannot be decomposed exactly into that conventional quantum mechanical tensorial product of two wave functions. This means that the two wave functions are bonded together forever until they are entangled. So ladies and gentlemen, again, what I see missing here is a clear identification of what Einstein considered clear limitation of quantum mechanics, and the admission of the need to surpass those axioms. Let me put it this way: the idea that the quantum mechanics can represent everything existing in the universe is no longer accepted by the majority of physicists nowadays. Even 100 years ago, Einstein had his own doubts. So the important issue is not to make an unbelievable stretches to see whether this can be represented with quantum mechanics, but admit the limitation. That's Einstein's view, and look for a covering theory. Hadronic mechanics is one of many different possible theories. What personally I believe is important is to look for the covering theory, because in any case, the representation of this phenomenon by quantum mechanics will be controversial, will be partial, epistemological, classical, but will be in any case outside the rigorous implementation of quantum axiom. This is essentially the view. Nowadays, the majority, as far as I know, but it could be wrong, of course. But the mystery of Weber persists. The mystery persists of the mechanism. What is the? Sometimes I don't sleep at night thinking about the mechanism. How can a particle here? I change the spin here, and this particle. This is a Vega. This is an Andromeda, a galaxy, and how can I change a particle spin here and this particle far away invert the spin? This is an enormous mystery, ladies and gentlemen. The idea that the dimension, the mystery of this complexity in this dimension, classical dimension, could be represented with entirely and exhaustively with quantum mechanics, the chances are very, very minute, in my view.
perhaps we have some difficulty with the term represented, right? Because the word represented to me doesn't mean explained, right? So that I still would say that it's clear that quantum mechanics does allow us to calculate the correlation Jesus mentioned in his slides. Like we apply the standard rules of quantum mechanics and we get this correlation of 0.85. And so quantum mechanics correctly predicts that, right? But it's not an explanation in the sense that it's not an explanation in the sense of a mechanical, realistic interaction. Right? So we need to make a separation between representing something and explaining something. So
Thank you.
So I think maybe that's why it appears that maybe that we interpret things in two different ways, but I don't think we really are interpreting, for example, EPR differently. I think both you and I, Dr. Santilli, both understand what Einstein said, but perhaps and the reasons why he said it. I think that, but I think that maybe we are using words a little differently, so that when we say that when you're saying that quantum mechanics cannot represent entanglement, what I would use the word quantum mechanics doesn't explain entanglement, because there is no mechanism that, but the mechanism is any mechanism. This was the argument that Jesus said, I think, was that any mechanism would be outside the system. Like it would be like if we describe these two particles as a system, we say it's a system, right? We put a big box around it, and even though they're from, one is in Andromeda and one is here on Earth, this box that describes the system has to include both of those. And when we make a measurement of the system, we make a measurement of the inputs and outputs of that box, even though it's extended widely over space. So accepting that the explanation can be a systems explanation, that is like that there can be correlations over a system, you know, as a how should I say that there's some measurement we can make of that system that shows that these things are correlated, even though they're a long ways apart, is not unusual, not unnatural, because we've accepted initially from the start that they are a system. And so it's only when we demand that the explanation has to be in terms of its parts that we run into conceptual difficulty.
Professor Page, I agree with you most sincerely, because often our disagreement, they're not disagreement, they're due to disagreement on the meaning of the words. So your distinction between representation and explanation is magnificent. Thank you. I will be much more careful in the future. But let me close this is very intriguing issue. Is the birth of this one of the most biggest mystery in the universe, is the birth of hadronic mechanics. It was built to try at least some empirical way to represent. But there is another extreme, huge controversy that I would like to close with, close at least my part of the presentation. I would like to close with this enormous controversy. Namely, there is the statement everywhere nowadays, which, let me tell you, I should not say so because it's not scholar, but it's considered political by a number of physicists, but I'm just reporting it. But namely, the statement that quantum mechanics predicts the entanglement. Ladies and gentlemen, I agree again with Einstein. There is this idea of correlation. Under no way the correlation predicts the entanglement. Absolutely. So there is, I must agree with a number of colleagues that there is there is a political aspect in this 1 century of history of so-called quantum entanglement, because what I can understand that some kind of correlation certainly is possible, but we see absolutely no prediction whatsoever, and no quantitative explanation that I know within the class of equivalence of the theory. And but what is at stake here? There is a stake, billions of dollars of contracts based on quantum mechanics, and that's why quantum entanglement everywhere, quantum computer, etc., etc. But on the long term, I'm not sure that this excessive weight on quantum mechanics to represent the problem of this complexity is really important. It really makes a contribution or a damage to human knowledge. I do not know, so I will leave it to your view.
But I think that this is similar to the way that the classical mechanics go in the time. First, Newton formulated classical mechanics only for particles. And then, in fact, only for one particle. Then, after it was necessary to add some postulates for think about systems of particles and more in the rigid body, for example, there was necessary to add more axioms, and after for continuum mechanics. All of this is classical mechanics. All of this is classical mechanics, and we can say based on Newton's mechanics. All of this, but more complex, because the system, when we try to apply the theory to more complex systems, there are additional suppositions that we have to make. And it's the same with entanglement. Entanglement is for two particles at less, at least two particles. And then we need more axioms. And I think that the use of tensor products, and when we say Hilbert space, I think that the Hilbert space have inside tensor product yet. And then if we use tensor product, we can explain how the system get in one entangled space. We can define and with physical process, that from two particles that are not entangled, we get one entangled systems. Then all of this is based on quantum mechanics. And for this, I don't understand the affirmation of Einstein that quantum mechanics not predicts the entangled states. I think that those entangled states are part of quantum mechanics when we speak for more than one particle.
Are you true, Professor Cruz? Are you true? Yeah. Well, again, this is, I'm interested in quantitative treatments, and yes, quantum mechanics can definitely represent those two particle as a single state. Yes, it can certainly represent. The problem again, so there is no doubt. There is no doubt that a form of entanglement is somewhat in between, is contained in quantum mechanics. In other words, if we exclude completely all we have gained from quantum mechanics on elementary part, we remove everything, and let's say, let's remove everything. Let's forget everything. Let's start from zero. Ladies and gentlemen, we will never explain the entanglement. So there is no doubt that whatever we learn from quantum mechanics remains fundamental for whatever future step. I consider the axioms. I cannot do more. The problem with quantum mechanics, that's why quantum mechanics, I agree with Einstein that quantum mechanics is an incomplete theory, because, and I agree with him that it cannot predict, because in the correct word by Professor Page, it does not explain how a particle here can influence a particle far away, unless we have a physical interaction among the two. This is a principle that I will never give up, otherwise otherwise I feel very, very uneasy. I have to understand what is the interaction for acting from one particle to the other at great distance. We need to know what is it. So that what is missing. That was missing in completely. So there is no question that quantum mechanics includes the entanglement in one form or another. But the point, however, I agree with Einstein, it cannot be the complete description of the entanglement. That's why Einstein said that quantum mechanics is incomplete. I agree with Einstein. Quantum mechanics cannot explain everything in the universe. Quantum mechanics is not good for nuclear fusion because they are irreversible. Quantum mechanics is a reversible theory, invariant on the time reverse. Nuclear fusions are irreversible over time, etc., etc., many, many other things. Quantum mechanics cannot, quantum chemists cannot represent how the valence bond. Those are two identical electrons. They're identical. How is it possible they bond together, two identical electrons? Any dream of trying to represent this with quantum mechanics? My God, ladies and gentlemen, I've been told years ago, I said, no, I'm not interested, not even listening in argument, because it's so far away from the principle of quantum mechanics. Quantum mechanics has been decided, constructed to represent the bound state of two particles with a clearly defined field, whether it is electrical or magnetic or gravitational. Yes, clearly defined. They attract each other, then yes. But those are we'll never describe two electrons that they bond each other into the valence bond, and etc. And this is only 2 or 3 out of many, many cases in which quantum mechanics cannot do it. So my view is any excessive emphasis in solely maintaining quantum mechanics for the entanglement, they may damage the advancement of the solution of other fundamental problems. The problem of the valence is fundamental to improve the combustion of. Is a problem that affects my children and my grandchildren because of the environment. Because in 100 years we have been unable to improve the combustion of fossil fuel. Why? Because we don't know. Because we remain with quantum mechanics at the representation of the valence. To maintain something that cannot possibly represent. Two particles are bonded together with an enormous repulsive Coulomb force. So there is a danger in being excessively emphatically in maintaining quantum mechanics for the entanglement in favor of, because all those problems that have been not resolved by quantum mechanics are all related. For instance, the problem that we are studying now with Professor Garrett on the using of the Bohm-Sinton variable and to represent magnetic moment. This is strictly related to the entanglement. It's because the proton and the electrons are deeply entangled. In other words, we are talking about a case in which of the magnetic moment of the electron, of the proton and the electrons does not represent the magnetic moment of the deuteron. Fermi and Weishaupt, they said because they use the word deformation. What we are doing with them, essentially, we are doing that those parts, when they are under strong interaction, they are so deeply entangled to imply an alteration of the notion of the concept of spin is altered by the entanglement. So what I would like to indicate to you is that the implication throughout the universe of the entanglement are beyond our imagination at this time. And the moment you see any of those implications, you move miles and miles away from any quantitative possibility, quantitative representation of a quantum mechanics. It's not even worth trying because it's hopeless. It's hopeless from the beginning, unless you concrete explanation, then you can try to improve it, but with no explanation of of the interaction, there's no hope. I'm not entirely, this is my feelings, I don't know. There are many, some of them, even the two elections, apparently the two particles are so deeply entangled to change that's my quantitative representation in 2001, that they're so deeply entangled that even the notion of a charge is altered. Let me put it in a different way. I've been unable to represent, in no way I've been unable to represent the attraction. That's the physical reality. We live because the molecules are bonded by electrons. Electrons are bound together into valence bond. Without the valence bond, we cannot exist. That's a physical reality we have to admit to remain scientists. I'm sure you admit that. But the point is this: I cannot possibly. I fail completely to achieve an attraction between the identical electrons by giving the notion of a charge, conventional notion of a charge. No, I found all sorts of impossibility. The only way that I got to quantity, still I don't know, like for the entanglement, I cannot say that I understand. No, I'm only interested in a quantitative representation. Any claim of understanding to the extreme may be dangerous. So the only thing I was unable to do is that the entanglement of those two electrons, this is the case, the two electrons, imagine those two to being very, very close to each other. The closer they are, the stronger the entanglement. Then they reach such a point in which the entanglement is so enormous to alter the very notion of the very structure of the charge and turn the two particles in the physical reality, which is a strong attraction of the identical electron. This is another consequence of the entanglement. I could make a long list of many other implications of the entanglement in astrophysics, in cosmology, and let alone in biology. It then becomes mandatory, exiting from quantum mechanics. In biology, human bodies we live because all the components of our body are entangled, precisely in this sense, here in this, but this is now becomes extremely rudimentary. It's sufficient to represent a living organism. It gives you the hint, the beginning. And this is reversible over time. We are irreversible. We are born and die. And the same for germs and viruses. So you need much more than that. But the germs, however, of life is the entanglement. Of so the implications are enormous in all branches of science that I know.
I think at this point is probably a good time to conclude our discussions for today. Again, we've gone over our time limit, so when we discuss those things that for me are so interesting, I completely lose the sense of time. But no problem. I think we've had interesting discussion. At this point, we don't have a proposal for discussion next week. Perhaps we can communicate by email about what our plans might be for next week, in the interest of sort of concluding today. So I just would like to thank you for participating, and thank you very much, Dr. Santilli, for your presentation. I think we would have to conclude that this discussion today was, as we said at the beginning, a discussion about entanglement in various ways, and so I think that's very valuable. I think maybe in the coming weeks, I don't know if anyone has a different subject outside of quantum mechanics that we would like to we should deal with. I think that would be very interesting. Dr. Sobczak, I know you have an interest more in applications, especially of geometric algebra, and there may be some applications of geometric algebra that are not so strongly related to quantum mechanics. So, I don't think that you should feel constrained. If you're if you're interested in some subject, or if you've been researching it, and you'd like to introduce that to our attention, I think even if it isn't about
Well,
quantum
I can
mechanics, I
think
think that
about
would be great.
Of course, the most mysterious part of quantum mechanics is exactly entanglement. That's really, nobody understands it completely, or that's what everyone's talking about. In fact, as Dr. Santilli said, that's related to the human body, or the way bees interact with each other, or
Yes, yes. At least
all kinds of things. How
But this-
nature,
but this
trees
is-
react with other trees.
Yeah.
It's
I'm afraid
incredible
we,
ideas.
yeah, I don't think we dispute that. In fact, that is sort of part of the conclusion, especially from Jesus's perspective today of dealing with systems. I mean, that the idea of a system is definitely inherent in biology, so that's. But in any case, I think we need to cut our discussion at this point, and I look forward. If any of you have comments or suggestions for future presentations, I think that would be great. We could also just decide to take a break for a while. So I think that's an alternative as well. So let's discuss that by email, and at least tentatively say we would meet again next week, but with the possibility that by email we might agree to.
Of
to
course, this
postpone.
is the final week where papers are due for the Zhyszko-Lejewicz Memorial Book. So that's something to think about
Yeah,
as well.
so that might be a good excuse not to have a meeting. But anyway, okay. Thanks again, and we'll see you again soon.
Thank you for allowing this very exciting meeting, and I appreciate your patience. I got I am Italian, so especially when something interesting, I got very exciting discussion, and I appreciate your patience for my enthusiasm.
No, not at all. Enthusiasm is definitely encouraged, to be encouraged. And that the important point is to be able to continue the discussion.
I have one final comment. I believe that our discussion has been very, very sedate and very, very civilized, because in history there are discussions on the entanglement, there are fights, and very Solvay. The
Yes.
fight Stein and Bohr are historical. So that I think they had no discussion whatsoever. They had the fight.
Okay, bye for now, everyone.
Thank you. Bye-bye. Bye-bye.
I